All right, I already explained that. Common divisors, we only consider monic divisors. And how about this statement? How trivial is it? I think too. I wrote it down. D of fg, all the polynomials, common polynomial is a monic. That is the definition written down. So you're looking at that definition. If you throw in multiply constant in front of it, C1 and C2 there, do you think that changes the, right? It doesn't really change it, right? It's just same as throwing in plus minus 1. If I'm looking at D of 1999 and 2000, 2071 like that, that's a divisor set. If I change that to like minus 99, that doesn't quite change the divisor set, right? Or GCD at all. That constant polynomial is doing that work in there. So if you throw in some constant polynomial, it doesn't change. Sometimes if this polynomial gets ugly, that you want to just clear out the coefficient by multiplying that number, sometimes it helps. It's a small lemma. Is that right? Okay. All right. What's the next one? I'm going to skip that part. I'm just going to state it here and explain what goes into that. I was looking for slick, easier proof, couldn't. There's this big gun. It has to be used to explain why there are finitely many divisors. But if you consider this two thing, they end up at only finitely many monic polynomials that divise both f and g, or just one polynomial, as long as it's non-zero, and there are only finitely many divisors in there. Why? And you can use something called fundamental theorem of algebra or unique factorization property. It seems like it's not so simple to explain why this is so. But I'm just declaring this as a fact, and one should just accept it. All right? If you have two polynomials, you have a question? Yeah. Yeah. Yes. Not number, mod polynomial. Yes, that works. Yes, yeah, which it was actually Euclidean algorithm, so it does work. Yes. Okay. Anything else? But we also saw that as a homework problem that I just explained all this thing as a homework. And there was only one polynomial with the largest degree in there. That's what we really care about, and that is the definition of a GCD. Yes, it's also in that slide. So that's what you wanted to copy down. Okay, good. All right. All right. Just like the homework problem, no one wants to divide this one by hand. And because you know how to divide one polynomial by another, we need a calculator, right? You don't want to, multiply four-digit number by four. Everybody use a calculator. So number theory calculator, we need it. Number theory calculator, and that's this SAGE. So we're going to start one at a time. This is a very simple thing I'm introducing in here. All right. You want to declare a polynomial variable to the SAGE. And this is how you do it. R is a ring dot x. X is going to be the variable for the polynomial. And that's going to be the polynomial ring with a QQ, so rational coefficients. Now, the SAGE knows that x is the main variable for the polynomial ring with a rational coefficient. So whatever you write down with x in it, you recognize the polynomial variable. Not unknown, not the usual computer variable. This is indeterminately recognized. So, and you can define f like that without parentheses x like that. That's how we recognize. F is not a function, it's a polynomial. F is just declared like this. You have to use a star in Sage. It's a Python-based language, so you must use star. And G like that. And F comma G is just checking that if I entered it correctly or not, and then it spits out like that. So I check that I entered it correctly by returning these to myself. It's not multiplication. This F comma G is just state F that I just defined and G separately. It's just like 3 comma 4. It's just repeated exactly what I typed. And one way usually what I do that if I typed it correctly or not to check it. Then you just go and write down GCD and it'll find the GCD for you. But we just spent some time to understand the meaning of this GCD of two polynomials, right? So it does it for you like that. So you can check your answer. Good. And because of that, the answer of GCD of these two polynomial, x squared minus 2x minus 1. But how do you do that in the test? You keep dividing one polynomial by another until you reach 0, and whatever the other guy is, change it into monic and match GCD. Good? So this one is really simple. Why is that simple? Because it's degrees 2, right? Actually, dividing is not painful. It is really pleasant experience. All right? So we will do that. All right. GCD is actually simple because you know how to factor this quadratic polynomial, right? Because of that, this answer is in front of you. So our main goal is to getting to that shape, right? Apply the Euclidean algorithm, get GCD, figure out Bezout's identity. Degree 3 or higher is pretty painful, so I can't do that in the test. However, this is okay. So stick to this algorithm. Don't try to figure out other slick method just to answer degree 2 case. This is exercise 5. Am I counting correct? What's your gut feeling? What's the GCD? Before you actually compute. What's your gut feeling? What polynomial divides both these two things? X plus 4? I don't see the x plus 4 divides that f. X plus 2? Anyone else? What's it going to be? No? Or how about doing it like this? I can't do any other way. When you're dividing two polynomial, this is how I do it, right? So I did it and recording. I need Q1, right? We're going to be using the Q1, and here's the R1. I recorded like that. Make sense? Do you know what to put in here? What are we going to divide next? R1 is going to divide G, right? So I'm going to put that G over here. How about that? G is coming over, right? Is that okay? And that's going to be Q2 and whatever the remainder you have there. One and negative, you have to subtract it, right? Is it 2? 1 minus minus 1 is 2. That's what you're looking at? Yeah, yeah. All right. I will just go to 0 until you're very, very sure. Like you don't want to make the mistake I made in last time. Make sure you enter the 0 and clarify all that rather than just getting used to it. So it's not necessary. If you know what you're doing, oh, I got constant there. I'll just stop here and that's my GCD. That's fine. But I did one more. If you divide any polynomial by constant, what is the remainder, right? Degree less than 0, negative infinity, right? So you had to enter 0 in there, but that's just clarification. So do you have an answer now? What is the GCD of these two polynomials? 11 is not the answer, but very close, almost. It's like 99%. What's that? No, it has to be monic polynomial. That's it. So what is the monic polynomial version of 11? What monic polynomial divides this 11, right? So monic polynomial, highest degree of monic polynomial divides that. It's the same thing as monic polynomial divides 11 and 0, right? What is it? 1. 1 divides 11, right, as a polynomial, and it's monic, but 11 is not monic. The coefficient is not. Yeah. So if you end up with 11x, GCD of 11x like this, what is the answer? Not 1, x, the monic version that divides 11 times x. Yeah, monic polynomial. So answer here is 1. Monic polynomial that divides R2, which is a constant polynomial 11, is 1. That's called irreducible polynomial. Yes. You cannot divide any further. Yeah. It's called irreducible polynomial. These two are irreducible polynomials over Q. All right. That's that, but we can't change that 11 to 1. You have to look at this chart, Q1 and R1 and Q2 and R2 as it is exactly, and you enter matrix version. Can you enter matrix version? Start from F and G, right? F and G are the degree 2 polynomial. What is the first matrix do we have to multiply here? 0, 1, right? 1, and what is the other one? Negative 1, that Q1 in there. What is the second one? 0, 1, 1, negative Q2, which is x plus 6, right? Yeah. And then by doing that, you're going to arrive here, I think, right? R2. Yeah. This is Q2 and arrived in R2. That's correct, yes. Is that right? Yeah. All right. We haven't reached the answer yet. This is what they're looking for. Fk plus GL equals GCD, right? But what is R2? R2 is not GCD, right? R2 is 11. So you're going to reach 11, not 1, but it's almost there. Write down what is 11 and see if you can actually GCD, reach the GCD there. Was that all right? Yeah. X plus 6 multiplied to f to degree 2. X plus 5 multiplied to degree 2g. If you subtract that, all the x's cancel and give you the constant 11. Fair enough? So do you realize that we haven't really reached that answer in there? Fk plus gl equals gcd. What is gcd? 1, right? So you have to divide everything by 11. And that is the final answer. And then you reach there. 1 over 11, x plus 6, that linear polynomial multiplied to f. 1 over 11 multiplied to x plus 5 and to that quadratic polynomial g now finally reaches this 1. And this is a lot of calculation. But these secret functions that polynomial multiply to give you 1 are coming from this. All right? Let me go back and copy that question and look at this answer and just compare that, reflect on one more time. All right? That's how you do. What is this statement called? Bezout identity for polynomial. All right? Once you reach that, the integer version is like real piece of cake. All right? All right. I have one more really strange exercise, right? So this is flashback, that's the answer. Flashback to calculus 2, and you have to think about what on earth is he doing right now? Flashback to calc 2, it says like this. Find the partial fraction decomposition of this guy. This is most hated question in calc 2. This most despised problem in the calc 2. Yeah. Partial fraction decomposition of this thing. What is the hint? That's right. Whatever we did has something to do with this one, right? So I want you to go in and stare at this guy really intensely and see what that is. That's our exercise number 6. Is that right? If they don't see it, don't tell them. They don't see it. There it is. Exercise 6. Or if you see it, do it. If not, keep looking at it until you see it. Here's a hint. That one and that one is the same one. Right? That one and that one's the same one. Yeah. 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 If there's a long division, it's not going to work. All right. Let me give you another interesting statement. This is how we approach the partial fraction decomposition problem in the calculus 2. You write this one like this, right? Any question about my answer? You just divide both sides f and g and cancellation gives the answer. That's that. So it goes like this, right? And write down ax plus b. Remember that part? And write down x squared plus 3x plus 1, and cx plus d. Now you expand them out, and you enter 4 by 4 matrix, right, to solve this thing, correct? But if you think about the logic behind it, it goes like this. Suppose this is possible. Suppose this is possible. Then I will find A, B, C, and D, right? If someone asks you this question, why is this always possible? What if I have degree 2017, I over here degree 275? Why is it possible to find this ABC? You look at this gigantic matrix, right? How do you know it's solvable? Uniquely, right? What is the answer? Do you know the answer? Bezout's identity. Because we show that it exists, right? Why does it exist? Euclidean algorithm gives you the existence of Bezout's identity. That gives you the solution to that problem. That gives you the existence of that. As you can see, is how profound this implication can be. If you're staring at this problem and look at that matrix, for example, if I play with the 3 by 3, you look at the 6 by 6 matrix, staring at that equation, wondering why is the 6 by 6 matrix is invertible, no idea, really. But Bezout's identity says is always solvable, therefore it's uniquely, it's invertible, right? So even though it started out as really simple, that, like 2 or 3 line proof from Euclidean algorithm, it has far-reaching implication if you keep playing with it. Yeah. So long division gives you the Euclidean algorithm. It's the coolest thing, right? Worth spending time on this one and fully understand what goes into that and what the implication is. It's still there. It has more implication towards the unique factorization, prime numbers, all coming from this Bezout's identity. All right. So I'll stop here today.